So we're back, and we're going to do the next 10 MCQs for March 18th. So let's start off with 11. The diagram shows 4 forces applied to a circular object, and they've asked, so they're basically asking whether the resultant force is 0 or non-zero, and whether the resultant torque is 0 or non-zero. So if you look at resultant force first, you have a 45 Newton force upward, you have a 45 Newton force downward, so they cancel out. However, you have two 30 Newton forces to the right and nothing to balance them. So in fact, you'll have a resultant force of 60 Newtons towards the right, which gives you, which you can basically cross out C and D. It's going to be either A and B because the resultant force is non-zero. Resultant torque might be a little more tricky. So you have to think, because here they probably have the same fixed point. And here, if it's the middle, they have the same perpendicular distance. So that's basically the radius. But you really have to think in which direction is this making the circular object spin? Is it making the circular object rotate clockwise or anti-clockwise? So 45 Newton force here makes it rotate clockwise. This Newton as well makes it rotate clockwise. So these two obviously won't cancel each other out. If we look at the 30 Newton forces in a different color, this makes it rotate clockwise. This makes it rotate, however, anti-clockwise. So these two cancel each other out. But these two, they just reinforce each other. They don't cancel each other out. And hence you have a net clockwise rotation, a net clockwise torque, or a net clockwise moment, giving you non-zero. So that's going to be A. A charged oil drop is held stationary between two charged parallel plates. Which forces act on the oil drop? Now, obviously, if it's an oil drop anywhere, on Earth, there will be gravitational force. So hence you can cancel out B and D. And your answer is A. This is a pretty simple one, because obviously if it's gravity, if it's weight downwards, then there has to be some force upwards to keep it stationary, right? It's not going to levitate like that. I mean, it doesn't have to. Exactly, like basically. So you're going to need some force that acts that opposes weight, and obviously, hence it can't just be gravitational force only. It has to be electric force and gravitational force. 13. In which example is it not possible for the underlined body to be in equilibrium? A, an airplane climbs at a steady rate. So if it's a steady rate, can we say it's climbing at a constant velocity?
Yeah.
If something's climbing at a constant velocity, well, then it means zero acceleration. And by force is equals to ma, you can figure out zero acceleration means zero net force, which means this is in equilibrium. So this is not our answer. You can think of this as the same thing as terminal velocity. So if a ball is falling at constant velocity, that means it is not climbing, but it is falling at a steady rate. It has zero net force. It is in equilibrium. So B, an airplane tows a glider at a constant altitude. Well, it is possible that this is in equilibrium, because if the altitude is the same, and let's assume that, I mean, they're asking where it's absolutely not possible that this can be in equilibrium. There are cases where if the airplane is towing the glider at a constant velocity, it'll be in equilibrium. So it is possible it'll be in equilibrium. C, a speedboat changes direction at a constant speed. What do you think of this?
This is not in equilibrium because direction change हो रही है, meaning velocity same नहीं है.
Okay, so it's a constant speed, but not constant velocity, because velocity has direction, and if it's not constant velocity, remember acceleration doesn't look at speed, it looks at velocity. So there will be some acceleration. Maybe the magnitude is the same, but there will be some acceleration, and hence you have some force, some net force, so it's not in equilibrium. You can cross out D as well, because if two boats tow a ship into the harbor, so let's suppose the two boats are pulling with some amount of force from the front, and the drag force, because it's of the ship,
The water.
oh yeah, of the
Yeah.
water, that's going backwards. So let's suppose the two, they're pulling at like 30 newtons, and the drag force is 60 newtons, like very arbitrary figures. But obviously in such a case it would be in equilibrium, so it is possible that it can be in equilibrium. Okay. 14. A car of mass 1100 kg is traveling at a constant speed of 15 meters per second up a slope inclined at 10 degrees to the horizontal. The combined frictional forces acting on the car are directed down the slope and are equals to W upon 5, where W is the weight of the car. What is the useful power output of the car's engine? So here we know that it's traveling at constant speed, which means whatever the power output here of the engine, and obviously whatever power output that pushes the car up the slope is useful power output. The wasted one would be stuff like heat and sound. So this
Yeah.
useful power output would be equals to, or whatever the useful force that's being applied by the engine to push it up the slope, would be equals to your frictional forces or your resistive forces down the slope. Hence, it's in constant speed. In fact, this would not just be your frictional force; it would also be some component of the weight down the slope.
As well.
Um, yes, so there would be a few calculations to do here. So let's first figure out your frictional force. I believe you can do that by W upon 5. So what is going to be
Yeah.
W? W is mg. So that is,
Is 11 to I think यहाँ पे 10 भी लेना तो चल जाएगा या 9.81 सीखा है.
well, I believe 10 would also work. It will give you a nice rounded value, but I don't like to take the risk. I just stick to
Yeah,
9.8.
हाँ, because A or B are pretty close together.
Yeah, so like let's just stick to 9.81. So this should give us our frictional force.
2158.2.
Your friction 2158.2 newtons. That's frictional force. Now, don't forget that if something is traveling up a slope, some component of its weight will also be acting down the slope, but also be kind of pulling it back. You can't forget that. So, and I believe that was given by W sine theta.
Yeah.
Yeah. So, in fact, it's just you can figure that you've probably done this in class, but anyways, so you have frictional force, you also have some component of weight which is given by W sine
W
theta,
sine.
where theta is the angle it makes with the horizontal. So here it would be W, whatever the value of W calculated, and sine 10 in degrees. Again, don't, if you're given your math, if then it has it in radians, well, that'll be a little unfortunate. Anyhow, so what would this be?
So that works out to be 1873.
1873. And now we can just,
0.8.
okay, point 0.8. Oh, we can just add these two um,
Yeah.
to give us our total forces that are pulling the car back, that are acting down the slope.
So it's 4032 newtons.
4032, 4000, okay, 4032, my bad.
4032.
Yeah. 4032 newtons. Again, let's visualize this again, because this is something I feel might trouble some people. So we've now concluded that 4032 newtons are acting backwards, which means 4032 newtons have to be provided by the engine to go forwards to ensure that it's in constant speed. So now think of it. Now you have the force it's giving. It's the force the engine is creating. You need power. There was a formula, I believe. What was it?
Force into speed.
P is equals to FV. No, F is equals
Yeah.
to PV. I don't know. I don't remember
P
the
equals
formula.
FP.
P is equals to FV. So you know 4032. You know V is what? 15, and
Yeah.
you just multiply. You multiply and you divide by 1,000 because you want it in kilowatts.
So yeah, we get C.
We're getting C. 15. An old-fashioned 60-watt lamp converts 95 percent of its heat supply, of its energy supply into heat. Pretty useless lamp, to be honest. Um, a 4-watt modern lamp has the same power output of the light as the old-fashioned lamp. And they're asking the efficiency of the modern lamp. So let's first try to figure out the power output of light of the old lamp. If it's 95% of the output is is heat, then 5% of the energy of the output will be light. So that is 5 upon 100 is
100.
6 into 60.
So that's 3.
3. So out of 60 watts, only 3 watts go to light.
Are you-
However, we know for a 4-watt, it has the same power output. So so from 4 watts, 3 watts light is provided. So to calculate efficiency, it's 75% kind of clear. But if you want to put it in the formulas, it's 3 upon 4 into 100, which gives you 75%. And you're good.
Yeah.
Again, ensure that this is a useful output, which is light. Don't take that 1 watt, which is whatever, heat or something.
That's heat, I guess.
Yeah.
और
16.
that छोटा लस ये
Yeah.
आवाज आ रही होती है. I think
Okay, so a bead is released from rest at point P and slides along the wire. The track loops around it's like a freaking roller coaster and forms a vertical circle of diameter 40. At point Q, the bead has a speed of 1.4 milliseconds. Air resistance and friction on the wire are negligible. What is the height h from which the bead was released? I think you have to do this through energy conservation and so on, because it's kind of impossible to do it through using equations of motion, because you aren't given the distance which it travels on the track, like this distance. You're not given this. So because you don't know this, it's kind of difficult to use any of those formulas that used to link acceleration and so on. So if you go the other way, if you go with energy conservation, we know here the energy is what? It's only GPE. It's only mgh.
gravitational potential
Yeah.
से start हो रहा है.
Yeah. Here, on the other hand, I mean, if you look at point A here it would only have kinetic energy. However, because here it's traveled a bit above, here it will have gravitational potential energy and kinetic energy. And as it goes without saying, because energy can neither be created nor destroyed, whatever we have here has to be equal to whatever we had here. It has to be equal. So let's try to form an equation for this. So you have, initially you had mgh. Obviously g is 9.81. M, I believe, will cancel out soon. Now,
Yeah.
and this is equals to the kinetic energy, half m 1.4 square, and the whatever the gp, whatever gravitational potential energy there is there, so which is mg. You know, h is 40, or should I write 0.4 because I've converted it into meters? You can clearly tell that if you take m common, you can cancel this out. So now all you have to do, you have to input g as 9.81, and you have to solve for h. It's as simple as that.
Yeah. So h comes out to be 0.5.
We're good to go. And again, it's meters here, which is why it was imperative that you converted this into meters beforehand.
Yeah.
A small.
Or speed be meter.
Sorry?
Yeah, meter per second.
Yeah, and even your
Speed be meter per second.
Yeah, he's right. So even your speed is in meters per second. 17. A small diesel engine uses a volume of 1.5 into 10 to the power 4 centimeter cube of fuel per hour to produce a useful power output of 40 kilowatts. Okay. It may be assumed that 34 kilojoules of energy is transferred to the engine when it uses 1 centimeter cube of fuel, and they're trying to figure out the rate of transfer from the engine of energy that is wasted. The rate of transfer of energy that is wasted is basically the power that is wasted. Because again, when you take energy upon time, that is your rate of transfer, which is basically power. So let's try to figure out your input power. You already know your output power. Output useful power is this. If you figure out your input power, you can subtract the two and get power that was wasted. So input power, they've told you that 34 kilojoules of energy from 1.0 centimeter cube. So X kilojoules of energy from 15 into, from 1.5 into 10 to the power 4. And you just cross multiply.
So that's like 1.5 into 10, 4 times 34.
Yeah, I would say just keep it in kilo because. Sorry.
बहुत large.
Yeah,
10,000 kilo.
10,000. I mean, can you give it in standard form?
510,000. So standard form में हो जाएगा 10, I guess 5.1 into 10.5.
Is this kilojoules or did you convert it? Yeah. So the reason we're not bothering to convert it into joules here is because your final answer also is in kilo, so might as well just stick to kilo, right? So this is your total input. What is it? Input energy. So this is input energy. You have
in 1 hour.
Yeah, and this is in 1 hour. So you want to figure out your input power, which is power is the energy upon time. So this would be 5.1 into 10 to the power 5. This is in 1 hour. So you multiply it. I mean, this was like 1 hour. So to go from hour to minutes to seconds, from hour to minutes, you multiply by 60. Then to go to seconds, you again multiply by 60. Multiply the denominator, I mean. So overall, it's going to be dividing. So if you do this, you can get your input power.
So the input power is 142 kilowatts.
Now, 142 kilowatts is the input power. We know that the useful output was 40 kilowatts, which leaves your wasted power to be 102 kilowatts. You just subtract the two. And again, to repeat, the rate of transfer the rate of transfer of energy is basically power. Energy upon time, that's your rate of transfer, is power. So when they're saying the rate of transfer of energy that is wasted, they're basically asking the power that was wasted, which is what we calculated here. That's A, and we can proceed. Two boxes X and Y have the same mass. Box X is lifted vertically through a height of h by a force of magnitude F. Box Y is pulled along a slope of the same magnitude by a force of the same magnitude. So there is the same force to reach the same height as shown. So what we can say for sure is that the GPE, the gravitational potential energy, is the same for both because they've reached the same height. So the same gravitational potential energy, same gravitational potential energy. Just on that, you can cancel out C and D. What can we say about the work done though by the forces?
The work done on Y is greater.
Okay, can you explain that?
वो hypotenuse distance ज़्यादा.
Can you dumb it down?
Okay, so the work done on X is just simply F into S, right?
Yeah, so like work done is force into distance. So here it would simply be, force into h. However, what Ashad's trying to say here, which, well, I mean, what he said, like, was force into whatever distance here, which is x. And remember, if this is the hypotenuse, it's obviously going to be greater than one of the sides, which is h. So hence, since there's a greater distance covered here, there's a greater work done as per this formula. Or if you're smart enough, you can simply say, distance other. But work done is.
Yeah.
Okay, this is easy. So the force extension graph of a metal wire is shown. At which point on the graph does the metal wire stop obeying Hooke's law? Wow. Basically, what does Hooke's law say? That force is going to be directly proportional with extension, right? If I remember correctly. So it's directly proportional if it forms a straight line out of the origin. When it stops obeying that straight line rule, that's the point after which it will stop obeying Hooke's law. So you get A. The diagram shows a large crane on a construction site lifting a cube-shaped load at a constant speed. A model is made of the crane, its load, and the cables supporting the load. Okay, that looks like a doesn't look like a nice question. Okay, the material used for each part of the model is the same as that in the full-size crane, cable, and load. The material is the same. The model is 1/10 full size in all linear dimensions, and they want to calculate stress, the ratio of stress.
Okay.
So what do you think?
Like you have to account for the volume of the load, the
Okay,
area of the cable, and the length of the wire.
okay. Um,
I
um,
guess that's it.
can we go
Or
with okay? Do you think we need to connect Young's modulus in this, because the isn't the Young's modulus the same if the material is the same?
yeah,
So what was the formula for Young's modulus?
force times length over area into extension.
Yeah. So stress
Stress over
into
strain.
stress over strain, basically. So you know this, that the Young's modulus for both has to be the same. If you want to go through that, so like L1 upon area 1 E1 is equals to area 1 E1. Area 2 rather. So 2 2. I believe the force wouldn't change then, or would the force change?
Force would change because आपका load भी फिर 1/10 हो जाएगा
Yeah.
ना.
Well, this is turning out. This is
But that
compli. Yeah, this is being a little complicated.
load हो जाएगा 1/1000.
Okay, so I think this is midway is becoming a little complicated. How are you doing it?
अच्छा, what I was thinking was stress का मांगा ना, so we just need to account for the force and area here, right?
Force and area. Okay.
Right. So, volume, since dimensions सारी 1/10 हुई हैं,
Okay.
right? तो volume जो है वो क्यूब के रेशो से कम हो जाएगा, like 1/1000 के रेशो से कम होगा,
Yeah.
right?
Basically
Which
one
means
tenth into
mass of
two.
the
Yes.
हाँ, which means mass of the load भी 1/1000 हो जाएगा.
Mass of the load. Uh, because to keep the density the same. Okay. So
Yeah.
so because the materials is the same, the density should be the same. So mass upon volume. So if volume is decreasing by 1/1000, then mass should also be multiplied by 1/1000. Okay.
And इसलिए force भी 1/1000 हो जाएगी because force is the weight of the load.
Yeah, so because it's a constant speed, right? So whatever force they're applying upwards is equal to whatever forces there is downwards. Downward force versus the weight, the upward forces can also be equal to the weight, and hence your force should decrease by 1/1000 as well, because weight is what? Weight is mg. G remains the same. M decreases by a factor of 1,000. So force
Weight
is,
also,
yeah, force or weight. And stress was force upon area. So
area of the cable.
area of the cable.
Yeah,
Yeah.
cross
Uh,
section. Yeah.
Cross sectional area. Okay, that's a better way to look at it. So before we go to stress, let's look at area first. Area of the cable would probably be circular. So the area is given by pi r square. But wait. We don't need to. Do we?
And
I don't think we need to look at that, do we? Or do? Although in linear dimensions it's going down. So do we need to look at radius? And
I think we should.
yeah. So because it's a linear dimension, right? So radius is something that's also being decreased by 1/10. So pi r square So this way, you kind of like think of it like this: 1/10, r square, which means area goes down by 1/100.
100.
So stress in the full size crane, let's just keep that as force upon area. In the model crane, if you think about it, it's in a model crane. If I write here, it's getting a little crowded, but stress was force upon area. Stress is now 1,000th of your force into 1/100th of your area, and if you simplify, uh, that gives you what? 1/10.
1/110. That gives you 10.
Yeah, so that gives you 1/10 stress, and if you keep here, if you keep 1/10 in the denominator for stress of the model crane, anything in the denominator flips to the top, so that is 10. You can just put that into your calculator, divide 1 by 1/10, you'll get 10. And that's it for this video. We'll continue in the next one. Let us just quickly check our answers though. So yeah, we checked, and so far we marked our answers correctly. And that's it for this video. We'll see you in the next one.